Welcome to Meshparts. Today we will see the design of experiments feature in the Meshparts software. This feature is located in the assembly frame below the assembly equations. This example is made with Bosch X-Rod profiles and Schneeberger wagon rail systems. The dimension of the assembly is parametric, so changing one dimension will automatically adjust the profiles and all other components accordingly. The structure shown has components and sub-assemblies. We see a block and a table component, a sub-assembly of wagons mounted on a rail, and a sub-assembly made with aluminum profiles. The wagon rail sub-assembly is used twice in the main assembly. This sub-assembly of profiles has further sub-assemblies which consist of profiles, and these profiles are actually connected using the positioning and connection feature in the mesh paths. We will solve this structure, check out the first mode shape and corresponding eigenfrequency. Besides, we will calculate the cost for this structure. The unit price of the profiles are given in the database. Now, for an optimal design, we want to maximize the first eigenfrequency of the structure and minimize the cost. For this reason, I shall change the profile components in the structure and solve again for the first eigenfrequency. I have defined a variable and initialized the value with the existing profiles in the assembly. The definition of variables are done in the assembly equation section. The definitions are as selected. Now, just for a test, let's say we want to change the selected four profiles in the structure. We have to change the value of this version 30 variable and update the assembly. This way we can change the variables in the assembly equation section and find the corresponding structure. The process can be automated with the design of experiments feature. In this design of experiments feature, we can find two tables. The first table above is for choosing the variable that we want to vary. With the button called Add Factor, we can amend rows in the table. Each row represents a particular variable, their minimum and maximum values and number of steps in between them. In the parameter name drop-down, we will find a list of all variables. Those are defined in the assembly equation section. We can select our preferred variable and define their minimum and maximum range and number of steps in between them. A row in this table appears as a design factor in the assembly. The second table below is called factorial table. Once we define our chosen factors in the first table, a combination of all these factors will appear in the factorial table. The values in the factorial table will appear according to our definition of the minimum and maximum value and number of steps in between them. We can edit the values of the factorial table right here, or we can copy the whole factorial table to an external text file for editing. After editing, we can paste the table back to here. We can remove rows from the factorial table using the button below. Every single row in the factorial table is a design point where each of the design factors have a value in their prescribed range. Once the factorial table is configured, the corresponding finite element models can be generated. We can use the active DOE design drop-down. Here each of the numbers actually represent the number of row in the factorial table, or instead we can use the generate models button below the first table, which will generate all the finite element models. Those are needed for this factorial table. Now we can check out the design points from the factorial table. Let's check out the design point 3. So we just select from the active DOE design drop-down. This will take some time, and afterwards we will see the corresponding model in the viewing area. In the same way, we can select other design points. The selected design point would be activated and shown in the viewing area. Any further analysis on this assembly will be applied on the activated model. Once we have all the design points ready, we can find the models in the Meshparts file explorer. The generated design points will have the name from the main assembly, amended with the design point number. We can see these here. Among these design points, we can select the preferred ones that we want to solve, and from the context menu, we can use the solve command. Once the solve operation is activated, the model will take the solution setting from the main assembly and solve. We can select multiple models from the Explorer, and from the context menu, we can solve all these models. When the solution is complete, we can see the results in the Meshparts viewing area. For this, we must select the Visualize Result option from the context menu. We can choose the HTML report to see the results in the internet browser. We can retrieve the model parameters as well. We can select single or multiple designs and use the context menu entry retrieve parameters. We can use the values of these parameters to plot curves. We see the blue and the orange curve here for the eigenfrequency and the cost of aluminum profiles respectively. The curves are plotted against to the design points. Besides, we have defined a weighted function as given in the plot. The red curve is for the weighted function. From the red curve, we find 3 local minima. These 3 are 3 design choices for the structure. Now let's say the design criteria for the assembly is 20 Hz and above. The 3 local minimas have 26, 20 and 12 Hz accordingly. The corresponding cost for these 3 minima are 500 euro, 460 euro and 290 euro accordingly. This is evident that the second minima is the optimum design. The corresponding design point is DOE 7. This is how we can use the design of experiment feature in the Meshparts software. This is a time-efficient alternative for large finite element models. We can conveniently observe the changes or dependencies of components in a large assembly. Thank you.